Hello, everybody. My name is Peter Warren. I'm going to give a quick presentation on binder jet technology for Lunar and Martian Regolith, both the promises and the technical challenges associated with this. I'm a graduate student at UCF. I'm making this video very quickly for YouTube, so I'll just do a quick presentation and try to go through this quickly. Okay. The outline of the presentation, I'll give a quick background on BJT, that is binder jetting technology. Then I'll get into the sintering investigation that we performed in the characterization, followed by powder binder interaction and some of the conclusions that we drew from this work. This is a piece of artwork that was made by one of my lab mates, Melos. Very nice piece of artwork showing the possibilities that can happen if we implement additive manufacturing and other types of manufacturing in extraterrestrial environments. In this case, this would be Mars. So background and challenges. Why use additive manufacturing on Regolith? Three words come to mind: adaptability, versatility, and scalability. We can create a lot of different unique geometries with additive manufacturing. The versatility means diverse material selection, so could possibly implement this on the Regolith material, which is in abundance, so that's a cost-saving thing as well. And then we have scalability. We can scale all of this up to create larger structures. Okay, binder jet additive manufacturing. The way that binder jetting works is we have a counter rolling pin here that this is the fresh powder stock. It will spin in the opposite direction and push this powder into the build platform. These two platforms are height controlled, so this one goes up. A fresh layer is replenished as this one goes down. And this is the binder that is distributed, liquid binder reservoir here, and it is distributed through an inkjet printer head or any type of liquid distribution system. And then you have an object or part here. One benefit to BJT is that no internal supports or no external supports. I don't know if you've used a PLA printer, you would know that it has to actually print removable external support for structures such as this, or structures that have something that would not be supported as it prints. In this case, the powder acts as a support mechanism. And then again, we have adaptable, versatile, scalable. And the key stages that we examined in this work are the printing stage, the powder binder interaction, the washing, we did not examine that much, and then the sintering is also a key phase. So we investigated those two stages of BJT. So the current challenges is sintering physics are very complicated. Sintering parameters have to be optimized to maximize density and other material properties. Sintering parameters include maximum temperature, the ramp rate, environment, and heat type. And then we have powder binder interaction. As we distribute the powder, or sorry, the binder, which is the fluid, onto the powder, the interaction will certainly affect the dimensional accuracy of printing. If the binder bleeds out further than anticipated or acts in an unpredictable manner, the final geometry will be affected by that. Parameters include, for the powder, grain size, packed density, powder shape, and material. And the binder parameters include viscosity, density, and material. So now let's get into the sintering investigation and characterization. We have process, property, and structure. The process that we wanted to mimic was the binder jet additive manufacturing process. The properties that we tested were compression, mechanical properties, and we used that doing compression testing and also simultaneous 3D digital image correlation. And we observed the microstructure using microscopic observation. This is how we performed the molding test here. We have 3D printed PLA molds, half shell printed on an Ultimaker S5 cylindrical half shell molds, 0.5 in diameter here, 0.5 inch, and 1 inch in length. Manually mixed them placed them gently into the molds, did not pack them into the molds due to binder jetting does not get any packing. It's just simply adhesive together through the binder material. Allowed it 1 hour and then put it in the pre-sintering process. This is a Martian Regolith sample. This is MGS provided to us by Regolith Labs at UCF. And it was also completed with the LMS1, that's Lunar Mare Simulant. The binder material is a saltwater binder, 6.25% salt by volume, and the mixture rate between binder and regolith was 1 part binder to 3.5 part regolith. So here we have the sintering process. This was carried out using this oven here, a tabletop sintering furnace. Curing temperature, that's pre-sintering, 200 degrees Celsius for 1 hour. Then we did 3 different sintering temperatures, 3 different sets. So that would be 1000, 1100, and 1200 C for 1 hour. The ramp rate was 25 C per minute. So because we have 3 different categories here, that is 15 total because we have a statistical weight of 5. And that would mean 30 total because we have 15 Martian samples and 15 Lunar regolith samples. Oh, and we can see some of the microstructure images here. We can see it at 200 times magnification. Here we have it at the powder stage, the green stage, 1000, 1100, and 1200 C. Now the powder to green stage, we can see a clear difference here. What the green stage indicates is that is when the binder has been applied to the powder, so the salt water has been mixed with the Lunar Mare Simulant or the MGS, and you can see that it does a pretty good job of binding the powders together here. We can also see that the difference between 1000 C and 1100 C is not substantial. A little bit of discoloring has occurred at this point in the sintering cycle, but when we sinter at 1200 C, we get much more thorough sintering. We have a glassy substance here that is probably from the basalt in the regolith, and a lot of carbonization. So when this sintered, the oxidation, because it was sintered in atmosphere, obviously played a role and oxidized some of the substance here. So now let's look at the shrinkage that occurred. Not a lot of shrinkage occurring at the 1000 and 1100 degrees C, but when we sintered at 1200 degrees C for an hour, much more shrinkage is occurring here. We're getting a lot of shrinkage in the height direction and not as much in the radial direction for both the Martian and Lunar regolith samples. Now, why was the radial shrinkage less than the vertical shrinkage? This is possibly from gravitational effects. Since as it is centered, the gravity is pulling down on it, and it was centered standing upright. Or it could be a built-in anisotropic properties during the manufacturing process, which is also a possibility, or a combination of the two. So now let's look at the strength properties here. Again, we have a pretty good compressive strength for cured 1000 and 1100, but much more substantial compressive strength. We're getting into the 20 to 30 MPa range for the compressive modulus. The 1200 degrees C sintering profile had the highest compressive strength, which is expected, and more pre and post processing would lead to higher strength, but our method is more simplistic. So if we look at some other research here in the table, we can see the different manufacturing techniques and a little bit of explanation into those techniques and the resultant compressive strength. This one here jumps out since it's very high at 152. The sample was dry pressed at 255 MPa and sintered for a total of 3 hours at 1100 C. So that dry pressing, pre-compression of the sample does ultimately lead to a higher compressive modulus. But using this method, there is very little pre-processing required to achieve a decent compressive strength. Standard brick here on Earth ranges from 6 to 82 MPa, so this is in that ballpark. And then the same thing with the Martian materials here. We have a little more comparison here. We can see that sulfur Martian concrete, which is a very promising process, has quite a good MPa as well. And our method in red here and our method in red here, 21 for the Lunar and 25 for the Martian material. Okay, so now we can look at the 3D digital image correlation that we did simultaneous with the compressive measurements, which we did on an MTS machine. We can see the standard stress-strain plot, stress on the Y, engineering strain on the X-axis. Failure occurs at around 2 to 2.5% strain for all samples. Catastrophic failure through crack formation and rapid propagation. The crack completely propagated through the sample in less than 0.2 seconds. Material stiffening occurs after about 1%, probably due to compaction. The DIC shows rapid increase in strain just prior to failure. The material is brittle ceramic, and also what these numbers indicate here, 1, 2, 3, 4, and 5, they are timestamps shown here on the DIC map. So to perform the DIC, we used 2 cameras, so it is 3D DIC. We put a speckle pattern on this and performed DIC in situ while the sample was being compressed on the MTS machine. The timestamps are right around the time of failure. 4, we can see the crack rapidly propagating, and at 5 we have failure. So we can see the drop off here in the stress strain plot. That's a clear indication of failure, and on the DIC measurements we can see the failure right there as well. And we put them a little closer together here for the Martian sample because the failures seem to occur a little bit faster. And 1, 2, 3, 4, 5, and here's the failure here. Okay, so now let's look at powder binder interaction. So the powder and binder interaction is when we allow the binder material to drop onto the powder material, which is just this is a simplified version of that. Obviously, they're not going to be perfect spherical particles, but the challenges are understanding binder deposition and penetration behavior. We want to maximize the green density because a higher green density results in a higher final density, and we also want to control the green geometry. To do that, we need to view and model the behavior in situ. So we need to create models and validate those models, determine the ideal saturation levels, and determine the ideal distribution method and rate. Now, saturation is a key variable here. I just put some very basic equations here to determine how to get to saturation. It is essentially the percentage of blue versus porosity here. So fractional density is density of the bed over theoretical density of the powder. Porosity is 1 minus that fractional density, so that's going to be a number between 0 and 1. And the saturation is the percentage, or the fractional, the percentage of liquid in the volume, and 1 minus the fractional density of the powder. So if it took up half of this white region here, that would be a 50% saturation. If it takes up all of this white region here, if that all gets filled in with binder, then you have 100% saturation. So our experimental setup that we did for this was we have a binder deposition method, a syringe of 0.25 millimeter gauge, a stepper motor system to control the amount distributed. We have the VHS 900F microscope, just an optical microscope. Measurements were taken at 30x, which isn't a very high resolution, but we wanted to be able to observe the entirety of the distribution of the binder. The data recorded here is in example images above here, and we gathered full video of binder deposition onto the powder. So image processing method, frame by frame, convert it to black and white, apply a Gaussian blur, determine pixel distribution. Okay, so here's our pixel distribution. Now we apply a binary thresholding method, single pixel cutoff, adaptive Gaussian weighted sum. Get this image here, and now we can draw a boundary around this, and here's our boundary, so we can track it now. Now we have an ability, if we do it frame by frame, to track the binder deposition area. Not a lot of measurements are available once we get this. After developing this algorithm, we can now get total area, total perimeter, surface roughness, fractal dimension, circularity, and I'm using this on other projects as well. But this method works very good, and this is a more complex one as well because of the kind of the color of the Martian regolith is difficult. You can see little dots here where it could be water, but with the Lunar, it actually comes out much more clear because it's a white versus slightly darker background. It's easier to segment the image there. Okay, so here we have some example videos of image tracking being performed. We can track the time, the wetted area, the perimeter. This is the material here, and the binder is a saltwater 10:1 ratio. Very large average particle size, very large particle size range. This is not an ideal powder to use for binder jetting. Some pre-processing may need to be done in order to have more control over the final geometry, and binder absorption is extremely fast, less than 1 second. Okay, so we can look at a few other videos here. We have a saltwater 10:1 by volume, and see how much slower this absorption rate is on this side. And on this one as well, this is a different method. This one's starting to get absorbed here. This is actually moving faster though, so that took 31 seconds. And this one still hasn't absorbed, but it's actually only at 8 seconds. The speed on these videos was different. Saltwater binder absorption takes about 18 seconds, so it's actually faster. In the titanium dioxide water, binder absorption takes about 30 seconds. Area absorption is more uniform compared to MGS. We have a nice uniform circle here. And the salt water is a dissolved solution. This one is a colloidal solution, so that means that it is a suspension. The particles do not dissolve. The titanium dioxide particles do not dissolve. The reason we experimented with titanium dioxide is because this is possibly a more feasible solution, and the physics are also very interesting as well. But there is possibly salt on the moon, but it's not been discovered yet, and there's possibly salt on Mars. It's not definitive, but there definitely is titanium dioxide in the powder. So if it can be separated out of the regolith, then that is a feasible solution and maybe more easily accessible than salt. But we can see that there is not a uniform distribution of the particles here, and the algorithm actually failed. I can train it to do a better job here, but in this case it did not, and it just tracked the remnants of the titanium dioxide as the binder material absorbs into the lunar regolith. So particle size range here, we can see that it's 0 to 30, much tighter range there, and an average particle size of 7 microns. So that's what leads us to a better, more uniform distribution of the binder fluid. So conclusions, a simple saltwater binder and sintering profile of 1 hour at 1200 C provided promising compressive strength measurements. The saltwater binder was suitable for both Martian and lunar regolith. Optimal sintering is between 1100 and 1200 C. The droplet dynamic studies showed that a finer powder provided a more uniform binder absorption profile. So That's pretty obvious in the binder jetting community. And image processing techniques developed for in situ measurement of binder absorption will benefit the modeling and help improve the binder jetting processes in general. So that's kind of projects that I'll be working on in the future, is applying those image processing techniques that we saw on the later slides to, binder jetting in a terrestrial application. Stainless steel, ceramics, binder jetting is a growing technology, and using these image processing techniques could benefit it and further develop it in general. But in this case, we did use them to examine extraterrestrial environments. So key takeaways: the effect of reduced gravity on sintering and droplet dynamics is uncertain. So that's something that we will have to study in the future. High suspended particle concentration led it to an uneven distribution of particles onto the powder. That's the colloidal solution, the titanium dioxide water mixture. The material is highly heterogeneous with angular grains, which prevented existing homogenized model. Multi-scale modeling will be required for further accuracy. And that's this sentence is talking about the modeling of the compressive behavior that we saw. It's hard to create a model, recreate what happened through using existing models, recreate the behavior that we observed on the compression testing and the digital image correlation. So multi-scale modeling will be required to get better material models in the future. The interaction between binder and powder is highly complex with multiple coupled physical phenomena. Validation will be challenging. So big breakthrough on that is that we do have a good observation method, and that is getting further developed. So that will assist in the validation of models in the future. And fine regolith powder is optimal for dimensional accuracy, but creates significant challenges with powder handling. So the handling of a fine powder is much more difficult. Spreading it thin into a thin uniform layer is more difficult than utilizing a larger powder. And that is all. Here's some references here. This is a paper that should be out by the time this video is published. It's the effect of sintering temperature on microstructure and mechanical properties of molten, Martian, and Lunar regolith. And this paper has been accepted into Ceramics International and should be published by the time this video goes up on YouTube. And that is all for this presentation. Thank you for watching. If you have any questions or anything, just leave them in the comments below. Thanks a lot.